In this video, we're going to focus on IR spectroscopy, specifically how to use it to identify functional groups in organic molecules. So let's compare the carboxylic acid with an alcohol. When you have a carboxylic acid, you're going to have a very strong, very broad OH stretch. This OH stretch, it shows up at a signal between 2500 and 3300 centimeters to the minus 1, which is a type of wave number. Now, the carboxylic acid also has a very strong CO stretch. And the CO stretch, it shows up at a signal of 1700 wave numbers. Now, you may want to write these numbers down because you'll need it in order to identify these functional groups in IR spectrums. Now, the alcohol, it only has the OH group. So it has a strong absorption around 3200 to 3600. So that's the OH stretch of the alcohol group. Now let's move on to our next two molecules, the aldehyde and the ketone functional groups. Both molecules contain the carbonyl functional group, and the CO stretch of these two functional groups is very similar to a carboxylic acid. It's around 1700. Now, the distinguishing feature between an aldehyde and a ketone is the CH stretch of the aldehyde. This signal here is the alkane CH stretch, which typically shows up for almost all organic molecules that has a CH functional group, and that's around 2900. So you'll see that for the ketone as well. But this part here, this identifies the aldehyde over the ketone. So the aldehyde will have a signal of around 2700 centimeters to the minus 1. So that is the aldehyde CH stretch. So that corresponds to that part of the aldehyde functional group. So that's how you can distinguish an aldehyde from a ketone, is the presence of this signal, the aldehyde CH stretch. Now let's compare the ester and the ether. The ester functional group has a carbonyl CO stretch of around 1700, very similar to aldehydes and ketones. The ether, it doesn't have the carbonyl CO stretch, but it does have a single bond CO stretch, and that is between 1000 and 1150. So something that you want to take into mind is that double bonds have higher wave numbers than single bonds. The C double bond O stretch absorbs at a higher energy than the CO stretch of an ether. And triple bonds have even higher wave numbers than double bonds. We'll talk more about that later in this video. For now, you want to take into account the type of carbon that is attached to the oxygen. That is, this is an sp3 carbon. Here, we have an sp2 carbon. So therefore, the CO stretch is going to be different. It's going to be higher. It's going to be between 1200 to 1300. And the reason for that is the resonance that can form here. So let's take this lone pair, let's form a pi bond, and let's break this pi bond. And now let's draw the resonance structure of the ester. And let's add the corresponding lone pairs. So we could see that the sp2 CO stretch of the ester has more double bond character than the sp3 CO stretch of the ether due to resonance. And why is that important? Well, as we've established, a double bond CO stretch has a higher wave number than a single bond CO stretch. So a CO stretch with more double bond character is going to have a higher wave number than the CO stretch with more single bond character. Now we do have an sp3 carbon attached to the ester. So therefore, we're going to have this signal as well for the ester on the left. We're going to have two CO stretch, an sp2 CO stretch and an sp3 CO stretch. But the ether, it only has the sp3 CO stretch. And so that's how you could distinguish between an ester and an ether. The first characteristic is the carbonyl functional group. That alone is enough to distinguish it. But the second thing is the presence of the sp2 CO stretch versus the sp3 CO stretch. Now let's talk about primary and secondary amines before we go into amides. Now the primary amine, which has two hydrogen atoms attached to the nitrogen atom, it will show up as a double peak with a signal somewhere between 3300 and 3500. Now the secondary amine only has one hydrogen atom attached to the nitrogen atom. And so it's going to have a single peak between 3300 and 3500. So that's how you could distinguish the amine, the primary amine, from a secondary amine. Now the amide, it does have the carbonyl functional group. And so we're going to have a CO stretch very close to 1700. And we also have the NH2 group, so we're going to get this signal as well, between 3300 and 3500. So to distinguish an amide from an amine, you need to look for the presence of the carbonyl functional group. And to distinguish a primary amine from a secondary amine, look for the double peak in the primary amine and a single peak in a secondary amine. Now let's talk about alkanes, alkenes, and alkynes. The alkane CH stretch, it has a signal of around 2900, which we talked about earlier. The alkene C double bond C, that signal, it's a weak to medium signal which shows up around 1660. Now the C triple bond C of an alkyne functional group, that signal is also a weak signal and it shows up around 2100 to 2200 wave numbers. Now the next thing we need to talk about is the CH stretch of an alkene and an alkyne. So the double bond CH stretch of an alkene, it shows up around 3000 to 3100. So relative to the alkane CH stretch, it's going to be slightly to the left of it. So here is the alkene CH stretch close to 3100. Now let's say if you have a terminal alkyne, and so you're going to have the alkyne CH stretch. This signal is even further to the left of around 3300. And so here is the alkane CH stretch, and then here would be the alkyne CH stretch. So this helps you to distinguish an internal alkyne from a terminal alkyne. And to distinguish an alkene from an alkyne, you could simply look at these two numbers. So let's talk about the effect of hybridization on wave number. So here we have an sp3 CH stretch. This is an sp2 CH stretch. And here we have an sp CH stretch. So notice that as the S character increases, the wave number increases. The sp-CH stretch, it composed of 50% S, 50% P. This is 25% S, 75% P. So as the S character increases, the wave number of the CH stretch goes up. Now, going back to alkanes, there's two other signals that you want to be familiar with. The first one is a CH3 bend, which has a signal of 1365 to 1385. And then the other one, it can vary between a CH bend, a CH2 bend, or a CH3 bend. And that can vary between 1400 and 1450. Now let's talk about the relationship between atomic mass and wave number. As the atomic mass goes up, the wave number goes down. So going from hydrogen all the way to bromine, we can see that the atomic mass is going up. But looking at the wave numbers, it decreases from 2900 centimeters to the minus 1 to an average of 550. And so there's an inverse relationship between atomic mass and the wave number at which a bond absorbs IR radiation. Now the next relationship that we need to consider is the one between bond strength and wave number. As the strength of a bond increases, the wave number goes up. We know that triple bonds are stronger than double bonds, and double bonds are stronger than single bonds. Thus, triple bonds will have a higher wave number than single bonds. We can see that in the case of alkynes relative to alkanes, in the case of nitriles versus amines, and carbonyls versus a C single bond O stretch. And it makes sense because more energy is required to stretch a triple bond compared to a single bond, because it's harder to pull 3 bonds than 1. And since wave number and energy are directly related, triple bonds will show up at a higher wave number in the IR spectrum. So that's another thing you want to take into account when dealing with IR spectroscopy. As the bond strength goes up, the wave number goes up. Now, another topic that we need to consider is conjugation. So here we have a ketone that is not part of a conjugated system, and it's going to absorb IR energy slightly higher than 1700. So this will be around 1720. Now for the conjugated ketone, it's going to absorb IR energy at a lower wave number. That is, in this case, around 1680. So make sure you understand that. Conjugated carbonyl groups, they will absorb IR energy at a lower wave number. Now the same is true for the double bond of an alkene. Here, this is a non-conjugated system, and so this alkene will absorb around 1650, 1660 in that area. Here we have a conjugated alkene, and so the absorption is going to be less. This one is going to be around 1600. So conjugated alkenes, they absorb IR energy at a lower wave number than regular alkenes. So remember, conjugation can reduce the wave number for ketones and alkenes. Now, it helps to remember something if you understand a reason why. Remember, we said that double bonds absorb energy at a higher wave number than single bonds. Let's look at the conjugated ketone. If we draw the resonance structure, we can put a single bond on that ketone. Let me color code this. And now we'll have a positive charge here. So looking at the double bond of the conjugated ketone, and let's compare it to the double bond of the regular ketone. Which one has more double bond character? The answer is this one. This one has more double bond character because it can't become a single bond through resonance. The conjugated ketone, it can become a single bond through resonance, so it has more single bond character. And now let's think about this. We said that double bonds have a higher wave number than single bonds. So because this ketone has more double bond character, it makes sense why it would have a higher wave number than the ketone with less double bond character. So as we've considered before, as the bond strength goes up, the wave number goes up. Double bonds have a higher wave number than single bonds. So that's basically it for this video. I wanted to give you a basic introduction into IR spectroscopy. Now, I'm going to be posting another video that has a few practice problems where you can apply the information that you just learned. So when you're ready, you can just go to the YouTube search bar, type in IR spectroscopy, practice problems, and then just type in organic chemistry tutor. It should come up. So that's it for this video. Thanks for watching.